Paulo Onoja is a quantum software developer passionate about building scalable and efficient quantum computing systems. Currently, he is interning at QWorld, where he is developing a framework for distributed quantum computing, focusing on realistic models for research optimization across multiple quantum processors. His previous work at QBraid involved improving quantum intermediate representations and integrating classical quantum workflows. With a background in software engineering and research spanning quantum simulators and circuit optimization, he aims to contribute tools and ideas that make quantum computing more accessible and practical. Before I give the word to Paul Onoja, can you hear us? Paul, can you hear us? I think we are having minor issues over there. Paul, can you hear us? Can you say something, please?
Yes, I can hear you. Can you hear me?
Thank you. Then I give the word to Paul Onoja.
Okay. Holy shit. Can you hear me? Okay. So our topic is, can everyone hear me? You guys can hear me, right?
We can hear you.
Okay. So our topic is on integrating QIR into a C-based quantum classical framework for efficient quantum computing. Please, can you go to the next screen for me? Okay. So this project, this presentation will start by going through the introduction of what QIR is and why it's important to have a C version of this project. We are going to talk about the mathematical framework, formalize the whole concept mathematically, talk about how the project was implemented and what results we gained. Then we are going to talk about advanced future work, like the future work and what can be added onto the project. Then we'll conclude the presentation. Please, next slide. Okay. As we know, we are currently still at the stage where we are trying to build up quantum hardware. We need standardized hardware for quantum systems. And so as not to, because this quantum hardware uses various different types of systems. Some use superconducting qubits and other things. So we don't want the software developer, the quantum software developer, to be stressed about the inner details of all these various types of hardware or hardware details. So we are trying to bridge that gap by creating efficient intermediate representation, compilers, transpilers, and the like, so that one can just write his quantum program in a high-level language, maybe Python, as some of these things exist already, Python, C#, Q#, Qiskit, and the like. So this is the gap that we are trying to fill by having a standardized bridge, as it's stated here, between high-level programming languages and low-level machine execution. That is based on the different types of quantum hardware. And next. Okay, yeah, I've already stated quantum system are fragmented, high-level languages here. So we are trying, this QR layer is like an intermediate representation where you get your high-level language, as I already stated, Python, Qiskit, Q#, and you convert them to QIR. This QIR is like, it's a borrowed term from, not borrowed term, it's a borrowed concept from classical computing, where we used to have IR, intermediate representations, but QIR is quantum intermediate representation. This intermediate representation can then be run, can then act as a standardized medium that every hardware system can get their code from directly. So the quantum software developer does not need to write code or a compiler for each hardware that he works on. He just needs to write his code, then the code will be compiled to the intermediate presentation. Then from there, it's just going to be the work of the hardware guys to compile the code accordingly to what they want. So what our contribution is in this system is that we present C. We present a high-level language in C that can be compiled to QR, so that, because currently we don't have any, like, as far as the research that we conducted shows, we don't have any method that converts from from C to QR or C to any form of country time representation. So this thing we are doing uses C to QR. That is one of the things we do. Then we present a formal mathematical framework that shows that our concept is correct. It shows correctness, proofs for gate operations. That means it shows that the quantum output is what is expected. We allocate qubits efficiently because that's the standard problem for most compilation techniques for quantum computing. We use intelligent qubit allocation, and we present a complete implementation that is based that we use Docker to present this implementation, so that it's present in the GitHub repo for anyone that wishes to use it. This is the architectural overview. You start with your C source code, just the normal C that you know. You use Clang or CLang, depends on how you want to state it. Then you with this CLang compiles it to LLVM-IR. We use optimization passes that is also present in LLVM-IR. After the optimization passes, we now use our custom pass that we created, the whole project, that is C to QR. We use the C to QR to transform. Please, can you go back to the previous slide? The previous slide. We use the C to QR pass to generate QR compliant IR. So that is the complete architectural overview. We get the C source code, compile it to LLVM IR using Clang, use optimization passes, then we get the SO file and run our C to QR pass on it, and now generate a QR compliant IR. Yeah, next slide, please now. Okay, yeah, next thing. Okay. We expose a minimal C API for quantum operations designed for simplicity and direct mapping to quantum gates. As you can see here, if you are just writing a C code, for example, for the first line, you can just use QC_H to represent your Hadamard gate. Then you put the number, and then this IDX is the qubit index. So this thing applies the H gate to based on the input you pass to it. For the X gate, C naught, that is multi-qubit gate, and the measurement, that is to bridge classical and quantum space. That's where it happens, the measurement side of things. Next slide. So from here, we see the source language, that is C, and the generated output language, the QR. You see the QCH is just what is in the initial slide, but more standardized, in a more standardized form. Where we see the C naught here accepts both the control and the target, while the rest that are single qubit gates just accept one specific output. The S and N are common for all. So the C, T control, then I is for the specific qubit one. Then the target language that we generate is QR. It uses alloc to allocate, get elements to fetch the element, release to release temporary qubits. And this QIS is the quantum instruction set. The instruction set is like the supported gates, or the supported gates if it's for a classical computer. Here to the supported gates for this quantum computer. Here the QIS is, we have the Hadamard, the NOT gate, the C NOT gate, and the measurement gate. Next slide, please. Okay, so this section here, from this formalization, the CR to Q, C to QR transformation, this section defines the mathematical foundation of our compiler, the compiler we generated. We represent the transformation of the whole thing as a function of this sigma LC of sigma that takes our C code and generates QR using which maps a C-based LLVM to a QIR compliant module M prime. The state of a quantum system with n qubits is represented in the Hilbert space here. This is where C syntax is this particular pure state is what makes sure our C code is still maintains quantum properties. This pure state that we define, make sure the compiler still maintains quantum properties based on these tensor products with n2 to the n. Please, next slide. Next slide, please. Okay, yeah, this is the question. So we designed an intelligent qubit allocation strategy called R-alloc, which automatically determines how many qubits a program needs. We do this by scanning all quantum intrinsic calls and extract qubit index one by one. You see the formal algorithm used here. We get the maximum of the both, whether it is statically defined or dynamically defined. We get the maximum of it and store it in nmax. So that is what we allocate. So in this way we make sure that we don't over allocate by maybe allocating more qubits than necessary, and we don't under allocate. So we check both statically defined qubits and dynamically defined qubits. Then we only allocate based on the maximum that we get. It runs in three phases, as seen in this pseudocode below. We have the static analysis that detects declared qubit count if explicitly defined. Dynamic index analysis, we pass every gate call to find the largest index used, as I said initially. Allocate them, then we now have the final decision where we allocate the maximum of the two to ensure enough qubits are available. Next slide. So next, this is the transformation rule. When our pass sees a gate, what does it do? When it sees a gate for unitary gate, that's single qubit gate. When our pass is replaced with its QR equivalent, because QR is defined by, it's Microsoft defined, and some other companies collaborate to come up with QR. So when our pass sees a H gate, we get the qubit, then we now apply these operations defined by the following mathematical expression. We apply it to each qubit that is gotten, that when we see the H gate. For the X gate, we do the same thing as we do with the H gate, but the application, the gate we apply, the X calculation we apply as defined by this mathematical expression here is different from that of the H gate. That is the only difference, since both of them are single qubit gates. Next slide. We'll see where it shines the most well. So the C0 gate is where it's the key example for the sophistication of our compilers, because it shows how it handles multi-qubit interactions. Where, unlike single qubit gates, where we have to be disturbed about both control and target qubits, and we have to manage them carefully. So how we do it is that, based on this pseudocode once more, how we do it is that the first step is to retrieve the target qubit, QT, yes, the target qubit, QT, using get qubit. We get the target qubit, this number one here. Then we allocate a small array for the control qubit. After we allocate the array, we now retrieve the control qubit and store it in this temporary control array. We retrieve the control qubit and store it here. Then we call the QR control X operation on the pair. As you can see, we call, because QR, as I said, it already has some defined semantics that we can borrow and use. We call the QR controlled X gate and apply it from the target and the target and the control. We apply the control on the target, then we now release the array. This to clean up memory. That is why we release, to show that we don't have memory leaks, because that is a consistent problem with programming in C. If you don't free up dynamically allocated memory, it comes bite you. So, and it's also defined by this mathematical expression. This is just the C0 defined mathematically. The next slide, please. So, as I said initially, this measurement translation captures the quantum to classical boundary precisely. This is where we move between quantum to classical. This is where the intersection comes in for this compiler. So it is done in these following steps again, defined by this pseudocode. We retrieve the qubits to be measured. Then once again, we invoke QIR. This QIR is already defined by the QIR specification. We invoke the QIR measure, a function that we invoke it to act on this on what we used on this QI that we got. We invoke it and we perform it on it. Then we compare the result against a predefined constant, result 1. Then we now convert the Boolean outcome into an integer representing the classical bit. So this way, this thing that we just do ensures correct probabilistic behavior that is identical to quantum mechanical measurement. Because when we compare the results, we can see whether we have gotten what is expected and what we have, because this is still just not ready to run. It's just on the QR. This is one of the ways where we can ensure that the QR steps we are taking is correct and it does not have any errors associated with our operation. Next slide. I see this, the correctness I was talking about, to make sure we don't have any problem. We prove that thing that we do where we are confirming it with a Boolean is proving that the transformation preserves semantics across all the program executions. This means that the C program and its transformed QIR are identical distributions of measurement outcomes. That means we don't alter the expected or alter its probabilistic state by applying our compiler. It still maintains that same state and does not alter anything that we don't want it to. So each gate rule preserves the unitary matrix representation. Measurement transformation maintains probability distribution, and sequential operations preserve meaning via structural induction. Our compiler, once again, does not alter the logical meaning of any quantum computation. Next slide. Okay, so now we are going to validate our approach with a Bell state generator in this slide. So this C code that we see here just applies a Hadamard on qubit 0. As you can see, this is how it will look like when you are writing it using the way you are writing your program. You see, using our compiler, this pseudocode. We apply a Hadamard on qubit 0, a C naught between qubit 0 and 1, and then we measure both of them. As you can see on the right, this is the Bell state. And you see that we get the entanglement, shows that they show perfect correlation with this entanglement. Next. There we are. So the QR structure, after you run the Bell states that I showed in the initial slide, this is the QR structure that is generated. This is what the compiler will emit with explicit runtime calls. It shows that 1, we have qubit arrays allocated using QR allocate array. So this is once again defined by the QR specification. We define our qubit arrays and allocate them using QR allocate array. Each gate applied through QR intrinsics like QRH, QR control X. So we see it here. We use this QRH as defined by the QR specification, QR controlled X, and QR measurement for the measurement. Then we also make sure that for memory safety, again, at the end, we release our array, that because this allocated array is what we define dynamically, not using the standard procedures. We define dynamically, so we have to release it at the end to ensure memory safety and QR compliance. So this is what generated QR, and this is correct QR for the Bell state. So it shows that our compiler generates the correct QR as it is expected to generate. Next slide. Okay. So this is the call graph. The transformation fundamentally alters the program's call graph. Initially, this is how it is. Initially, we just call. Initially, when you write it, what the C program language see is that you have a function QCH, QCC0, QCX, QC measure that are all called in your main function. But after our compiler runs on it, you see that we now do have things like allocating array or the C0. We get element pointer for each and every qubit that we are trying to allocate. We call H gate, Hadamard gate for when we want to apply the Hadamard gate. C0 gate too, we have the control X. We also use measure the measurement. Results equal, that is to confirm the correctness of the QR generated, and release array for memory safety and to make sure our code, our QR is compliant with the QR specification. Next slide. Okay. Okay, so this is how our program did in this is just the metrics we used to summarize the whole code and program and expected output of programs we use. Pass overhead is less than 10 milliseconds because it shows that even though, of course, with using an extra pass on your program will increase the speed, but the speed is minimal. It expands the code QR by just 4 times, which is acceptable for in the early stages of QR. It is acceptable for to just have 4 times more code than usual than the original C code. So the complexity is O(n), which is superb for computing terms. It is not exponential or even polynomial in any way. It's just O(n). System requirements: you need to have LLVM, C++, the usual. Use CMake for building, and then QR runner. It's a program that runs generated QR. So all these are also actually contained in the Docker file or on the GitHub. So if you use the GitHub repo and you just use the Docker file there, this environment is automatically created for you. In the example we showed earlier, we have 31 lines of C code and we got 124 lines of QR. That is like 4 times as stated here. And the runtime was just 7 milliseconds, which is quite okay. And all transformations validated with QR execution engine. All this shows that the QR was correct because we ran it on QR runner and it shows that it runs correctly. Next slide. Okay, this is a comparison with existing framework and why this work is actually important. You can see we see Q Sharp, Qiskit, Circ, all these ones. Q Sharp is domain specific. I think it's for Microsoft. Qiskit is based off Python. Circ is based off Python. Python, as we all know, is quite slow and it's because of how flexible it is. Python has its good side, but because of how flexible it is, because of things like doc typing, that means you don't state the type that you are trying to do initially. Python is quite heavy and it's not portable. It's not portable. I mean, so but this our work using C is quite portable, more portable than the rest of them. Does not depend on any particular system. It is native to QR, just like Q Sharp. But before you get QR via Qiskit or Circ, you have to use an external transpiler. You don't need that with our current work. And the overhead for generating the QR is minimal compared to Circ and Qiskit because they are not native to it, which is quite high. And Q Sharp, because of how large it is as a language, it is medium level. The unique advantages we present here is system level access. Embedded devices can use this because they are more familiar with languages like C, or maybe a time in the future where we can use quantum computers for various types of devices because we don't know where. Real-time control is current now with quantum hardware. Direct QR generation, no intermediate translation. This work, if you write your code in C, you just get the QR directly. It is integrated with LLVM because LLVM is I think, is most probably the most widely used IR currently. So it is integrated with it. We have access to all LLVMs, optimization passes, transformation passes, and the like. And minimal runtime, you just use LLVM and QR, and those are the only overhead generated. Next slide. Okay, opaque pointers. LLVM version 15 and above introduced opaque pointers, meaning all pointer types are represented simply as PTR or pointer. This change removes type level information like qubits, like you can no longer specify the type of a pointer, which is quite necessary for languages like C that we are trying to work with. But since we are obviously related to LLVM, with LLVM 15 and above, opaque pointers are just fixed. You just state a type pointer. You don't need to state what type of pointer it is. So we had to fix this because it is important to know the type of pointer we are trying to work with. How we fixed this was making sure that function declarations define expected pointers as types explicitly. So the function that we use defines the function pointer type explicitly. We do not rely on LLVM to generate it for us. All load and store operations specify their element types. Before you store anything, any function that loads or stores something has to also specify the element type, the type of element it is trying to store or load. The type of element it's trying to store or load. Then we ensure type safety. We ensure that type safety is maintained through careful IR construction. Because as I said initially, we ensure that type safety, because that is a feature this PTR eliminates type safety because now we just use opaque pointers, but we make sure that we check for each program what type of element it's expected or what type of function. What the function states what type of element it needs and states it explicitly. Next slide. This slide was supposed to be behind, but I'm still just going to explain it now. Just a mistake on my part. This is how we get our allocation. This is how we allocate these things for multi-phase allocation of the qubit allocation. We define qubit allocation into a multi-phase analysis algorithm to compute the optimal qubit count, like the amount of counts. But this was supposed to be in the previous slide. We first use static analysis that detects the amount of qubits. The amount of qubits first. If we first have static analysis, detects constant declarations. It detects what, like, okay, if it is stated explicitly, we use it. If it is not stated, we use dynamic index extraction, where we iterate over every quantum operation to find the largest qubit index used. When we use, if it is stated explicitly, we use the ones that say explicitly. If it is not stated, we loop over each and every one. One of the reasons why we have O of N2, we loop over each and every one. Then we merge, we choose the max of the two. As I said before, this is supposed to be initially, because I talked about this before, we choose the max of the two. This makes sure that we balance flexibility and safety, ensuring that even dynamically index qubits are allocated properly. This is very important for Q-based, C-based program, because as I said before, dynamically allocating memory is quite dangerous in programming languages like C, where type safety is very important. Next slide. Wait. We successfully designed and implemented a C2QR compiler framework that bridges the gap between system-level programming and the quantum software stack. Our LLVM pass provides a lightweight, performant, and extensible pathway for C-based quantum development backed by rigorous mathematical foundations. One of the key achievements we have is that this is the first novel compilation framework. This is according to the literature survey we performed and known to us, to the best of our knowledge, this is the first of its kind C2QR compiler. It is portable. We use intelligent allocation to make sure that multi-qubit gates are allocated optimally, because we use the R-alloc as defined initially. We make sure that our QI is correct. Then it is working. It's validated with QR runner, and all the code is available on GitHub, where people can just run it fast using Docker. Next slide is the references. Okay. Next slide. Okay, future directions. What we can do to enhance this current compiler pass is to add rotation gates, because it is not currently present. As I stated, the instruction set earlier was just the X gate, the Hadamard, the C0, and the measurement gate. We can add rotation gates, extend the gate set by adding Toffoli gates, that is the CC0, phase gates. Then we can also add classical control like measurement and branching. We already have measurement-based branching, and branching based on measurement. Then the long-term possibilities is like trying to compile the QIR to hardware backends directly. Because as I said, QIR is important for hardware backends, because hardware backends can just talk to them directly and get the output. We can try to make a compiler from the QIR to IBM counting systems or IonQ trap computers, or that to give direct FGPA control. We currently also don't have error correction. We can, or anyone interested can work on that. And optimization, we can add further passes to optimize the QIR generated, because currently we just rely on LLVMs optimization passes. We don't have any custom optimization. Next slide, our references now. Next slide.